Okay, that's the beginning of a new topic for you. So far, we've been discussing one facility problems, either the absolute one center problem or the absolute one medium problem. Now, we're going to actually have more than one. P will be the number of facilities, and so first, I'm going to discuss the P-medium problem in a general network context, and then we'll switch to the center location problem. And then we will start specializing to the tree networks, because tree networks are polynomially solvable for both types of problems, while the general network problem for either one is NP hard. Okay, so there's a difference in computational level of difficulty. So first, let's begin with P-medium. Let's again assume we have an embedded network N with vertex set V, edge set E, and I'm going to assume the vertices are numbered again 1 up to N. And we may assume there's a weight Wi associated with the ith vertex. We may assume all are non-negative. And so this is part of the input data. And you've got your distances defined by shortest path length, so on and so forth. So everything is this, the stage is essentially, well, it's the same as before, as in the single facility case. So what we're going to do in this case is, rather than choosing a single facility, we're going to choose P facilities. These are identical facilities in the sense that they provide the same type of service. So as a demand point, it doesn't matter from which particular facility you get the service, as long as you get it in the least costly way, which means you normally go to the closest one. Okay, that's the idea here. So P homogeneous facilities are to be located. And homogeneous meaning here that they are uncapacitated, if you want to take a note of that. And they all provide the same type of service. Uncapacitated and same set of services. So that you don't have any preferences between the facilities other than the accessibility. All right. So what we're going to do is we're going to locate these points or the facilities at points, say x1 up to xp. These are the locations of the facilities we want to choose from. Each is a point in the network. And what I'm going to do notationally is I'm going to put them in a set capital X, and I'm going to call that the set X consisting of these P points. Because this is a set, by assumption they are all distinct. They don't overlap or they don't coincide. Okay? That is a minor point, but nevertheless, when you have identical service facilities, if they coincide when they're uncapacitated, it's not really meaningful. Then you have simply P minus 1 facilities if you have two coincident facilities. So that's why we have that assumption. So given this, we know the distance between any 2 points x and y is well defined. This is again the shortest path length between points x and y in the network. This is computable. and by taking each point as an artificial vertex, so to speak, so that it becomes the sum of the lengths of the edges as well as sub-edges that are contained in a path. So you choose the smallest length such path. All right, so given this, we define the nearest distance between a given vertex vi and the point set x by this notation. This is the distance of vi to a closest element of capital X. Let's write that down. Distance of vertex vi to a closest element of X. Now, when X is given, of course, this simply becomes the minimum of P numbers. Those numbers are the distance between X1. X1 is the first member of X and VI. The second one is the distance between X2 and VI, so on and so forth. The last one is XP VI. So you simply find the smallest of these numbers, and that gives you the closest distance. Now, when you go through the literature, as you have been doing, sometimes you will see this definition embedded into the definition of the optimization problem we're going to deal with, which confuses the issues sometimes, okay? But it's better to keep it this way, that there's an a priori definition of this distance, which actually requires an optimization in essence. Well, it's not an optimization, but you have to find it given that X actually precisely determines the locations of the xj's. Nevertheless, when you start varying X, of course, that becomes a variable thing, okay? All right, so given this, if you multiply W with that distance for a given I, and if you interpret Wi to be the number of trips that you expect to take place per unit time between demand I or vertex Vi and the closest facility in X, that's going to be the total number of times. Well, Wi is the total number of times, so Wi times that will be the total distance you incur due to that leg of travel during the year, or whatever your unit time is. Okay? So given that, total distance due to serving VI, that's what it is. And you've got such total distance for each one. Typically in the literature, again, instead of people typically call this, rather than total distance, they call it total cost associated with the ith demand point. Of course, that makes sense, because if you have a per unit transportation cost per, say, kilometer, then it's just a matter of multiplying this with a scaling factor, which turns it into a cost, assuming that the per kilometer cost is the same throughout the network. Of course, if it varies, then you're going to have different things, different scaling factors along the edges if it differs from one edge to another. So what do you do? In that case, rather than using the actual lengths of edges, you may simply multiply the actual length by that cost parameter per unit, which would turn it into a cost cost element for that edge. So rather than talking about shortest path distances, we would be talking about least cost paths, or the least cost of traveling from X to Y or from Y to X symmetrically. Okay, so these are not things that should bother anybody. When you make assumptions of that sort, they really don't make you lose generality. All right, given this, with no loss of generality, what we want to do is we define a cost function or total cost function f of x, which is simply the summation of these total distances due to each demand point. Okay? And what is the problem? The problem is to minimize this total cost as a function of capital X over all x's such that x is a subset of the network. In other words, it consists of points from the network with additional stipulation. X, the cardinality of x, or the number of elements in x, is equal to p. These are your restrictions that you should obey when you do your search. And given this definition, we say if, say, x star is such that, first of all, it is feasible with p points in it, and additionally, the objective value you obtain for x star is less than or equal to the objective value you would get for any other x for every x subset of n for which x again has p elements in it. So if you have a set of p points in the network, and if the objective function is the smallest it can be, then of course that's an absolute median solution. So if x is such that for well, actually there's no period here, the statement continues, then x star is called an absolute p-median of n. If x is restricted to subsets of V or a finite set that contains V as a subset, then it's called a vertex restricted version of the problem. So in that case, the p-median problem we have is the vertex-restricted p-median problem. In the former case, when there's no restriction, it's the absolute p-median problem. Now, for the one median case, of course, we had this proof that says that there's at least one optimal solution coinciding with a vertex. Okay, we had that. That's the Hakimi's node optimality property. So the natural question to ask is, can we extend that to the multi-median case or the p-median case? The natural answer is, maybe it just occurs to you that it should be the case. Well, actually it does. It does also serve in this case that the vertex set is a dominating set, meaning that the vertex set supplies at least one optimal solution, like in linear programming the extreme points, the set of extreme points, supply at least one optimal solution. So likewise here, the set of vertices supply at least one optimal solution. Now, does anybody see an immediate proof of that? Well, actually, it takes a number of steps to do that. Okay.
If we actually know that for 1 million we have the property. So if we place 1 million and assign a certain number of nodes, assign a certain number of demand nodes to that, we can deduce them from the general network, and we end up with another general network.
I didn't get.
We can also place another million. So if we place all of them simultaneously, we can apply the property p times, which will not violate the property. The actual proof actually comes from triangular inequality, but it's too long to be cited here.
Okay. Well, it's. I think you have a point, but maybe you're not making it too clear. So what you're saying, well, I don't want to say it because then, of course, I would be, it's better to say it in a much clearer way. Did everybody get the idea? Or Ataberk, you want to say it one more time? Because it wasn't very clear. I got you. I know what you have in mind, but it's not too clear. You want to give it a try?
I just want to say that if I am not misunderstood, if I've been misunderstood, solving the problem for one medium problem will not give the solution of p medium problem. Solving that problem step by step will not give the p medium problem, I think.
Yes, that's what's not clear. Actually,
We can argue that every optimal solution partitions the network into p sets, p distinct sets that we could like each one is a median problem, like p networks. Then we could solve we can show that for these subnetworks the vertex are optimal because we know that. So since the function, our objective function is sum of these functions, then we will not lose optimality.
Okay.
If we can do this for all partitions, then I will get at least one optimal solution.
Okay. Is that what you had in mind?
Basically.
By what you said?
Is also another explanation is also that the assignment of medians and the remaining demand vertices generates a forest. And of course we have trees, and for trees we know that it's...
Yes, the thing that was not clear in what you said was, or misleading was, you seem to suggest that you would solve by locating one point at a time. If that's what you exactly had in mind, that would be, in general, suboptimal. Because if you locate one, then, of course, it's not clear which particular vertices will get the service from that particular one. You can consider all possibilities, so on and so forth. But that's a bit misleading if that's what you had in mind.
No, what I had in mind was
okay.
Forest property, but
I see.
Explain it without saying forest.
Okay. If you had the forest idea, I think that's what also John is referring to. He's referring to that as subsets of demands or subsets, subnetworks, rather than forest. But okay, yeah. All right. So the main, you've got the main idea. That's the. Actually, we can immediately make use of the one medium property, the fact that there's at least one medium, which is a vertex. Then we can extend that to this case. It requires a little bit more precise arguments, but let's go ahead and state that as a property first. So there's at least one subset X of the vertex set consisting of some P vertices such that the cost for that X, let me make it a particular X, okay, let's just put a bar on it. The cost you obtain for that particular subset of vertices is less or equal f of x for all x subset of n with x cardinality x equals p. Okay? So there's at least one optimal solution on the vertices. The proof. The main idea is, again, to utilize the one median vertex optimality property. So what we're going to do is, let's begin with some optimal solution. So let X star be an absolute p-median solution. If X star is a subset of the vertex set, then you're done. So assume it's not, okay? If X star is not a subset of the vertex set, partition the demand vertices, or partition V into P subsets, V1, V2, so on and so forth, VP. These are subsets of V. They are disjoint, that's what partition means, and collectively they exhaust all elements of V. Okay? All right, so where? So how do we partition? That's the idea. Where Vi consists of all those vertices, say Vk in the vertex set. Let me put that in, such that the capital D relative to X star Vk is defined by the ith x, okay? So it's defined by dxi with a star, okay? Now, this is not a sufficient definition for partitioning because you may have actually some ties between different xi's. They may be at the same distance, at the same closest distance from a given Vk. So you need to also give a rule for breaking ties. So let's just, you can give any rule, but let's just assume that the ties are broken in favor of smaller indices, okay? Meaning that if a vertex Vk has tied facilities, each of which is closest, then you place that vertex into the subset whose index coincides with the smallest index among the tied elements. Okay? That's what it means. All right, so let's do that. And this is, of course, for each I. Okay. So let's begin with f of x star. That's optimal. So it's less than or equal to each f of x. Okay. Well, actually, before I do that, I need added other definition. Sorry about this. Let's just erase this because I haven't finished what I wanted to say yet. Let xi bar, let's just define a single facility solution relative to the ith vertex set. So let xi bar be a vertex optimal solution to the one medium problem defined on the vertex subset or vertex set capital Vi. Okay, this is defined for each I. So what that means is xi bar solves the following minimization problem. You try to minimize over all points x in n, except that rather than using n, you may restrict your attention to vertices. But I'm going to write it as an absolute medium because I already said that. Where did I say that? It's a vertex optimal solution. Okay, it's a vertex. It's an optimal solution coming from the vertex set. All right. So that xi bar solves minimize x in n, where what you want to minimize is wi. Let me use wj here. Wj cap dxj. Dx vj, j going from 1 to n, where the weight wj cap is the same as the old weight for those vertices that belong to the partition under consideration, and the weight wj cap is equal to 0 for vertices not in capital Vi. Okay, so you only took those vertices in capital Vi, retained their weights. All the other weights, you just made them equal to 0. So that when you solve the problem in this way, you can, of course, obtain non-vertex optimal solutions as well. But we picked a vertex optimal solution because we already know that there's such a solution. And that's my xi bar. Please make sure you've got that word there. Okay, so define x bar to be this set. So I took the x star solution. I decomposed my network into p subnetworks, and then on each subnetwork I solved a single facility problem, and I made sure that each single facility problem is a vertex solution because there's such a solution, and I put them together and formed my x bar. Now we have f of x star, which is by definition how much? Well, it's the summation wi capital D x star Vi, I going from 1 to n. That's the definition of f of x. And this one is, of course, let's write it this way. Okay. If you take the summation, break it down into the partition V1, V2, etc. Then the first partition gives Wi times. Now for the first partition, these capital D's are equal to dx1 star Vj's. Sorry, that's a J. Plus. The last one will be summation Wj dx p star Vj, where again Vj is restricted this time to capital Vp. Okay? That's simply from the definition of my partition, which all right, so let's see what we want to do from here. Now, when you look at the first sub-problem, if you replace x1 star with x1 bar, what happens to this summation? This summation is greater or equal that summation. Does everybody agree with that? Okay. So this is clearly greater or equal the summation. Again, in the first partition, Wj dx 1 bar Vj. Why? Because x1 bar is an optimal solution to the one median problem. So this is a one median objective function value for the first partition. At some point, x1 star. That x1 star may or may not be an optimal solution to that one median problem. For that reason, that summation is at least as great as the first summation here. Likewise, each other summation is greater or equal than the corresponding summation we have here. There are too many subscripts here, so if I make a mistake with all these subscripts, please be careful and point that out to me. Yes?
Do we mean by making summations from Vj J, we make the summations over J's such that Vj is...
Yeah, that's okay. Okay, that's what we mean. Sum over those vertices or vertex indices within that set. Yeah, that's what it says. All right. Now, what do we know about the fact that if I replace each small d here with capital D x bar, that small d will be greater or equal capital, right? Because from the definition of capital D, that's what it is. All right, so this is greater or equal the same summation Vj in V1. Wj is still the same, but I'm replacing that one with capital D x bar Vj. So it's important for you to understand that that small d is greater or equal the capital D here, because capital D is defined to be the smallest of such elements. Okay? That's how it is defined. So for that reason, of course, it will be less than or equal to any one of those elements. If you don't follow the notation, sometimes these are difficult because of just the notational barrier, or you forget actually how things were defined. When you forget, then it short circuits, okay? But so you come back here, where am I? See, if you take this as x bar and these as x1 bar, xp bar, etc., that one is less than or equal to each one of those elements. So we're using that here. Plus, the same is true for each corresponding summation, so we just write it again. Now, of course, what we're doing is simply summing over all vertices. You don't have to pay attention to the partitioning anymore, of the weighted distances between the point set x bar and each vertex vj. That's what we're doing if you collect all those summations together. So how much is this? That's equal to f of x bar by definition. What did I show? I showed, well, we have some inequalities, but x bar is certainly greater or equal f of x star, because x star is assumed to be optimum, so it must hold this way. Now, so we began with f of x star. We ended up with f of x star, which means all the inequalities in between hold as equalities.
Shouldn't that be the other way around? Fx star is greater than or equal to fx bar.
F of x star is optimal by assumption. So its cost is less than or equal to any other solution. This part is from the optimality of x star. And of course, you should have a good explanation for every other inequality or equality. All right, so obviously then this is equal, and x bar is also optimal. The idea is pretty much actually, I think it occurred to essentially probably all of you, except that John, I think, gave the main structure of the proof, and I just elaborated on that. Okay, so that's what it is. So, the important consequence here is that from an infinite search, you've reduced the original problem, the absolute p-median problem, to a finite search. That finite search, of course, consists of all p-element subsets of V. It's large. So, one way to do it is to enumerate by picking each p-element subset and do it. How much time would that take? Or what would be the order of computation for that? Total enumeration. From n vertices, you choose p vertices. So you've got so many possible ways of doing this, which is a large number. And for each one, what do? You compute a summation. First, of course, you must compute the capital D's, and then you compute the summation. To compute a capital D, how much time do you spend? You need the minimum of p elements. Of course, assuming that you've already computed the distances at the beginning, by pre-processing. So, assuming that you have the distance matrix, the vertex-to-vertex distances, each computation of capital D requires p order of p operations. Once you've got them, you multiply them with the wi's. So that's n such multiplications, and then you add them up. So each evaluation takes O(n) time, as far as I can see, okay? So total effort will be O(n) times n choose P, which is large. Nevertheless, it's doable, at least for small problems, okay? Now, let's give an integer linear programming formulation for the problem. What time do you have? We have 1 minute. Okay, let's take a break first, and then let's talk about the formulation.